Okay, November 2022, paper 6, variant 3. Question 1. A student investigates the dimensions of a boiling tube. Dimensions of a boiling tube. Okay, the student pours a small amount of water into the boiling tube and measures the height, H note, from the bench to the initial water level. So first of all, she had some water in this boiling tube and she measured the distance from the bench all the way to the water level. So just one precaution, one very important precaution would be to take the reading perpendicularly, right? Take the reading perpendicularly. Why? To avoid the parallax error, right? To avoid the parallax error. And then the student uses a measuring cylinder graduated in centimeters cubed to add the volume of water V 5 centimeters cubed. So each time she keeps on adding 5 centimeters cubed to the boiling tube. And each time she measures the new distance, the new height, right? Each time she measures the new height. For the value of V equals 5 centimeters cubed, calculate and record in table 1.1 the increase in height H. First of all, can I measure the height H? Measure and record the new height H. Can I measure the new height H all the way to this point? Yes. Can I measure the height? This height. What would this height be? Well, this height would be 4 centimeters, right? It would be 4 centimeters. If your reading is slightly less, it's okay due to the printing, but it should be 4 centimeters. And then, can I find H? Can I find H, which is the increase in height? The increase in, yes, it's H minus H naught, or 4 minus, it was 2 point, 2 point what? 2.6. 4 minus 2.6. Yes, 4 minus 2.6 is 1.4. So this is H, or the increase in the height. Can I plot the graph? V slash centimeters cubed, so V slash centimeters cubed on the y-axis, and H slash centimeters on the x-axis. And let's plot the values. V 5, 10, 15, 20, 25. So can I start with 0? Yes, you can start. I guess you can start with 0. 0, 5, 10, 15, 20, 25. Okay, it's okay. What about H? 1, and you need to reach 7. So I think you have to start with 1, 2, 3, 4, 5, 6, 7. Yes, you have to start with 1. On the y-axis, if you wanted to start with 5, it is okay. It is okay. Let's go. Let's plot the points. 5 and 1.4. 1.4 and 5. So this is 1. Let me zoom in. 1.4 and 5. This is the point. And then 2.9 and 10. 2.9. Okay. 4.1 and 15. 4.1, 15. Here it is. 5.7, 20. 5.7. Okay. 20. And 7.0 and 25. This is the easiest point. 7.0 and 25. So here are the points. Your points. Can I draw the line of best fit? Yes, and measure the gradient and calculate the gradient. Okay, so the line of best fit would be yeah, like this. If you want to continue the line all the way to the y-axis, it's okay. So this would be a nice line of best fit. I have one above the line, two of them below the line, so it's okay. It's kind of balanced. Can I find the gradient? Yes, to find the gradient, you have to draw the triangle method using the two furthest points. using the two furthest points. Again, do not use two very close points. You have to use two very far away points. Let me remove this line. And to find the gradient, it would be 25 minus 5. 25 minus 5 over 7 minus 1. 0.4. 20 divided by 3.57. This is the gradient. 3.57. Can I find D, which is the diameter of the boiling tube using this equation, 4g over pi? Okay, square root 4 times 3.57 over pi. What is square root 4 times 3.57 over pi? This is 2.13. 2.13 centimeters. Excellent. So just why is it important for the student to add a small volume of water at the start of the experiment? Again, in the start of the experiment, she added some water, didn't she? Yes, this is the initial water. And then we measured H naught, the initial height of the water. If she hadn't done that, would the experiment have been accurate? No, it wouldn't. Why? Why? Because this part of the tube, it's still circular, right? It doesn't have a constant volume. It does not have a constant volume. That's the problem. It doesn't have a constant volume, doesn't have a constant shape yet. Not a constant diameter yet. Right? So the diameter inside the tube isn't constant. Diameter inside the tube isn't constant. For example, it's getting larger until it becomes constant. Oh, here it's constant. All of this is still constant. So the diameter inside the tube isn't constant. That's why she has to add some water to make sure that the diameter is constant. And then when she keeps on adding 5 centimeters cubed of water, she can measure the new height and measure the diameter based on these readings of the height. Okay, so the diameter isn't constant of the tube. That's one student. Another student uses this experiment with the same apparatus to measure D for a small test tube of a diameter approximately 1.2 centimeters. He adds water in volumes of 1 centimeters cubed at a time. State and explain one reason why this is not an accurate method to use for this test tube. The first student was adding 5 centimeters cubed. This student is only adding 1 centimeter cubed. Is it accurate? No, it's not accurate. Why isn't it accurate? Why isn't it accurate? Because 1 centimeter cubed is very small, right? The change in the height is so insignificant. The change in the height is quite insignificant. That's the problem. The change in height is insignificant, right? The whole experiment is based on measuring the change in the height. If the change in the height is only 0.1 centimeters or even less, then it's very, very insignificant. Student performs an experiment on the cooling water and beaker. He investigates the effect of the color of the outside surface on the rate of cooling. Beaker A is covered with a black card. Beaker B is covered with a shiny metal foil. And I guess we know the difference between a black surface and a shiny surface. Record the room temperature. This room temperature is 22 degrees Celsius. Soon pours a volume of 150 centimeters. Describe one precaution that can be taken. Okay, one precaution is to take the reading perpendicularly. Take the reading, okay, perpendicularly to avoid the parallax error. Right? He records in table 2.1 The temperature every 30 seconds repeats the process for beaker B. Can I complete the table headings? Yes, I can complete the table headings. Seconds, degrees Celsius, and degrees Celsius. And then write a conclusion stating if the color of the outside surface affects the rate of cooling in the beaker or not. Does it affect the um, yes, does it affect it? Yes, it does affect it. How? We need to state the values. Okay, we need to take the readings of the values. 86 and 68.5. What's the difference between 86 and 68.5? Minus 68.5. This is 17.5, right? This is a huge difference. 17.5. When you had the shiny metal, it was 85.5 and 78.5, right? What's 85.5 minus 78.5? A much smaller difference of 7 degrees. So yes, it does affect it. Huh. Right? If the color affects, yes, it does affect. Yes, it affects. Okay. We can say that the black surface increases the rate of cooling, right? The rate of cooling. And then we need to state the numbers with the black card. With the black card, it was 86 minus 68.5, which is 17.5 degrees Celsius. And for the shiny metal, it was 85.5 minus 78.5, which is 7 degrees Celsius. Okay? Can I find the average rate of cooling for beaker A in the first, okay, at 180 for the whole 180 seconds? Yes, beaker A, which is 86 minus 68.5 divided by 180. 86 minus 68.5 divided by 180. What is this number? 0.097, right? 0.097. This is the first rate of cooling. Do not forget the unit. Degrees Celsius per second. Can I do the same for beaker B? Yes, it was 85.5 minus 87.5, wasn't it? Yes, 78.5. 85.5 minus 78.5 divided by 180, which is 0.039 degrees Celsius per second. Okay, so it states that the black card is thermal insulator. When he added the black card, it was a thermal insulator. He thinks this will affect the result because it's a thermal insulator, so might increase or decrease the rate of cooling. So just an additional experiment to test this theory. To test this theory, how can I do an additional experiment? All you need to do is just paint it black, right? Paint it black. Instead of using a card, physical, you can just paint it black. So paint the beaker black. So just two variables which should be kept the same, two variables, same initial temperature, and same volume of water. Okay, same initial temperature and same initial same volume of water. State how the cooling rate of beaker A from additional experiment is likely to compare with XA if the student's theory is correct. So if the student's theory is correct and the card was an insulator, so he removed the card, he painted the beaker black, and he repeated the process, and he measured the new rate of cooling. Can I compare? Can you think of a comparison? Should it be greater? Should it be less? Will it be the same? Between these two readings, these two rate of coolings. You removed the card, you removed the insulator. He stated that it was an insulator, right? He stated it was an insulator. So do you think It would be higher or lower? Yes, it would be higher. So the rate of cooling would increase. Rate of cooling would increase. That's based on his theory, right? That's if his statement is correct. So the rate of cooling would increase. Okay. Um, why? Because the if it's a thermal insator, okay. So no more insation, no more insation would result in a greater loss of heat. When you remove the insation, it would result in a greater loss of heat. Okay. Hmm. In question 3, we have a circuit. On figure 3.1, complete the circuit to show a voltmeter connected to measure the potential difference across the parallel combination of P and Q. So you have voltmeter across P and Q. Soon measures the potential difference across the parallel combination, voltage and the current. The voltage is 1.4 volts and the current is 0.76 amps. Can I find RPQ? Can I find the resistance of P and Q while they are in parallel? Yes, it is 1.4 over 0.76. 1.4 over 0.76, which is 1.8 ohms. 1.8 ohms. Do not forget the units, please. Connects the voltmeter to measure the potential difference across the resistor S. Can I take the reading? Yes, this reading is 3 point. Okay, this is 3.8 volts. Can I find the resistance S? So 3.8 divided by the initial current, which was 0.76. Okay, divided by 0.76, what's 3.8? Which is 5.0 ohms, right? 5.0 ohms. Soon connects the ammeter to measure the current IP in resistor P. Then he connects the ammeter to measure IQ in resistor Q, right? Read the value of IP and IQ. What is IP? IP is 0.2, okay, or 0.20 amps. IQ is 0.52, right? 0.52, which is as high as someone, anyway, 0.52 amps. Agent suggests that IT should be equal to IP plus IQ. Is IT equal to IP plus IQ? Let's see if this suggestion is correct. What is IP plus IQ? This is 0.2 plus 0.52, which is 0.72 amps. Is this the same as IT? IT was 0.76. Are they close? They are close. Are they within the limits? We need to calculate them. So 0.76 divided by 0.72, which is 1.05 or 1.06, 6%, definitely within the limits. So yes, they are. Yes, they are equal. 0.76 and 0.72 are close and within the limits of experimental accuracy. Right? Okay. Soon changes the circuit and uses a variable resistor. Can I draw the variable resistor? Okay. This is the variable resistor. Mark with an X on figure 3.1 where a variable resistor is connected to control the current. in resistor S without affecting the resistance of either of the parallel branches. Okay, where should I add this variable resistor in this circuit? The variable resistor should be at this point, for example, right? It will affect the current, it will affect the resistance of S, right? If you want to put it on this side, again, it's okay. It will not affect P and Q. Current in the circuit can be controlled by connecting a range of different resistors in place of resistor P and Q, right? You can connect different resistors. State one disadvantage of this method instead of using a variable resistor to control the current. So if you add resistors in parallel or in series or whatever, the current will be affected, yes. But if you use a variable resistor, it would control the current directly, right? Why? Because it would be why would this be a problem instead of why would using several resistors be much of a fuss? Well, because it's more difficult. It's more difficult to keep on adding resistors in parallel or in series or whatever. It's more difficult to add several resistors and take many readings, right? So we know for the experiment we need at least 5 readings. So instead of adding 5 resistors, you can just use a variable resistor and change it 5 times. That's it. It would be much easier, wouldn't it? Yeah, I think so. Moving on to question 4, plan an experiment. You have a squash ball. Okay. The student investigates the effect of temperature on the bounce height of a squash ball. Okay, would it affect the bounce height or not? I do not care. What I care about is planning this experiment. So plan an experiment to investigate how the bounce height of the ball changes as the temperature of the ball rises. As the temperature of this ball rises, we will not put the ball directly above the Bunsen burner, for example, and measure its temperature. What? No, we will not do that. You cannot do that. You will burn the ball, right? This is a squash ball. It's made of rubber. It will melt. How can you increase the temperature of this squash ball? Hmm, By putting it inside a beaker with hot water, right? Place it in hot water. Exactly. So this is my experiment. I have the beaker. I will put the squash ball inside the beaker, make sure it reaches the temperature, and I will keep on changing so the range of values. Let's write down. What am I changing? I'm changing the initial temperature. So the range of values, the initial, okay, temperature of the water and the ball, right? The initial temperature of the water and the ball. Can I use different values? Yes. Let's say 50 degrees Celsius, 60, 70, 80, and 90 degrees Celsius. So you have at least 5 values for the initial temperatures of this ball. And then list any additional apparatuses you need. Okay, what about the key variables? The key variables, the most important key variable in this question is what? Is the height from which you drop the ball, right? You're not measuring the height, you're measuring the height of the bounce after it bounces back. So the most important key variable would be the height of the drop. You can say the same ball, yes, the same. Would the same volume of the water affect it? No, it would not. Think about it. Do you care about the volume of the water? No, I do not care about the volume of the water. I care about the temperature of the water. I care about the temperature of the water. Whether it reaches 50 degrees in 1 minute or it reaches 50 degrees in 10 minutes, it's not my problem now, right? I do not care about the time at all. I care about what? I care about it actually reaching the temperature, the needed temperature. So the height is the most important uh, controlled variable. Controlled variables. Hmm. The height of the drop. And then, what about the missing apparatuses? Let's check out the apparatuses that we have. A selection of some squash balls, standard heating equipment. So you have the Bunsen burner and you have the cold water. We need a thermometer and we need mm, a measuring tape or a ruler, right? We need a thermometer and a ruler, right? Okay. Can I state briefly? Can I write down the steps? And then can I, yes, can I write down the water bath? We don't, no, we don't need the water bath, no. Can I write down the steps? Hmm. What are the steps for each temperature? Okay, or you can say put the water in put the squash ball. Okay, the squash ball in the water. Make sure it reaches the same temperature, okay, as the water. And then drop the ball from a fixed height, from a fixed height above the ground, from a fixed height above the ground, and measure the height of the bounce, right? Height of the bounce. That's it for the steps. What about the table? Can I draw a table? Yes. Don't have that many things to draw on the table, right? In the table, but the most important thing is to write down the initial temperature, the temperature in degrees Celsius, and the height of the bounce, the height of the bounce in centimeters, right? And then, last but not least, we can write down a conclusion, a very simple conclusion for each temperature, for each temperature. Repeat the experiment. Okay, repeat the experiment and take average. Record the readings in the table. Record the readings. Okay, in the table and compare the results. Compare the results using a graph or by plotting a graph of the temperature versus the height of the bounce. Height of the bounce. Okay. Okay.